welcome back to Quantum Mechanics. Today is Quantum Mechanics Lecture 7, and we'll be going over ladder operators again. So what's a ladder operator? Well, recall the time-independent Schrodinger equation as looking something like this. Oh, darn it, dude. So, this is the essential form of the time-independent Schrodinger equation. D squared phi dx squared minus constant phi is equal to the energy function multiplied by psi, where psi is, of course, our position-dependent wave function. So, what is a ladder operator? Well, this would be m squared omega squared h bar squared. This looks oddly suggestive. V squared can always be minus IV. So, we tried that procedure last time, and it turns out if we take it here, this gives us a plus, the raising operator, and this here gives us a minus, the lowering operator. We still don't know why these are called that, so we'll motivate it this time around. So we have these two, but of course there's a catch. Operators don't work or play as nicely as regular numbers. So when you actually factor these, it's going to give you what? Should this be x? I'm pretty sure that should be x. Yeah. So when you actually factor these, what does it give you at the end of the day? Well, it's going to give you 1 over the square root of 2m times d dx plus im omega h bar x. And this gives you 1 over the square root of 2m d dx minus im omega h bar x. But there's a catch. Not only are these operators not commutative, but this is actually equal to them multiplied plus half h bar omega, which we worked out last time around. So, here's what we're going to do. Today, we're going to justify why they're called raising and lowering operators. Or in general, ladder operators. So, what do they do? Well, right now, I'm going to show you that A plus psi is actually a solution to this equation, just with a different energy. So let's assume 1 over 2m d squared dx squared plus m squared omega squared h bar squared x squared psi is equal to E psi. Now I'm going to let this be E naught, psi naught, psi naught. Now I'm going to show that A plus psi naught,
don't touch your nose.
it's itching a lot, is actually a solution to this equation with a slightly different energy. First of all, note that an operator and a bunch of constants commute, but an operator doesn't always commute with other operators. So here's what we can do. This is, of course, equal to A minus A plus A plus A minus plus, oh yeah, it's on this side, sorry, I'm done. Plus m squared omega squared, 1 half h bar omega. That right there. So, if you take this, now we take it and put it in, and we get 1 over 2m A plus A minus A plus half h bar omega a plus. Remember, we can shuffle this around to the front and call it a plus half h bar omega instead. And suddenly, we can now factor out a plus this way. We can bring it outside. And then, note that this fella right over here is actually equal to what? Well, a minus a plus is equal to a plus a minus plus h bar omega, which means that this can actually be written as a minus a plus minus half h bar omega plus h bar omega psi naught. So this collapses in and becomes E naught from the original. And so this is the solution. Oh, the 1 over 2 has gone away a long time ago. I apologize. And so this gives us that a plus psi naught multiplied by E naught plus h omega is equal to E a plus psi naught. Specifically, if psi naught is the solution to the Schrodinger equation with energy E, then a plus psi naught is a solution to it with E plus h bar omega. And you can probably also guess that the lowering operator, even though it's an exercise left to the watcher, brings it down by h bar omega. Now, you probably have one question here. H bar omega is constant. And so, ostensibly, you can keep raising it with no problem. But what happens if you just keep lowering it? Obviously, E is not infinite, which means there's some K in which E minus K h bar omega is less than 0. But that is absurd. That doesn't make any sense. How can it happen? Well, here's the thing. Absurd things are perfectly fine as long as the solutions to the absurd equations are also absurd. What we mean by that is this equation has no physical meaning. That's all right as long as its solution has no physical meaning. And so that means the solution to this equation has to be non-normalizable. There's option A, which proposes making the integral of this infinite. Unfortunately, that has to be crossed off because that would just make everything above it infinite as well, including all of the ones with physical meaning. Or we can go with option B, which would be to make the integral 0. That is, there is some final wave function after which, if you apply this operator, it becomes 0. Pretty simple, right? So, what we're going to do now is find that ground state. And that's actually fairly simple to do, because if you plug in, that gives you 1 over the square root of 2m multiplied by d dx psi naught minus, let me take a look back, I m omega h bar x psi naught. And this looks intimidating, but it's solvable by separation of variables. You write this side as d psi naught dx is equal to I m omega h bar x psi naught. Then you bring this over to this side, and you bring all of this over to this side. You integrate on both sides, and you get ln psi naught is equal to I m rad 2m omega h bar x squared over 2. And so you raise both sides to the e. Well, technically you raise e to both sides, and you get psi naught is equal to this giant constant, e to the giant constant multiplied by x squared. Or another way to put it would be amplitude multiplied by e to the x squared. This is the ground state. And so, every state above it, which we denote psi n, is just going to be this when we repeatedly apply the raising operator to e to the x squared, which is actually very nasty. So, there's no good closed form for it. But that is why we call it a ladder operator, because it's a ladder. You can go up step by step by step. You can go down step by step by step. But there's a bottom rung, even though there is no top rung. So that's it. Thank you everyone for watching, and we'll see you in the next one.